Good morning all. Welcome to the EasyPower Tuesday refresher. Appreciate everybody attending. Welcome everyone to the discussion. Today's topic is mitigation technologies for arc flash incident energy. And just as a caveat as we start this, we're not recommending or even suggesting specific solutions. The focus frankly is on using EasyPower as a tool to look at your system and consider alternatives. So again, welcome, and let's start with a poll question. So the first question is basically trying to understand what your specific requirements are today and what's motivating your attending this particular session. Give about 5 more seconds to collect people's inputs. It could help kind of expand some of the topics that we're going to be involved with. Appreciate everybody for the feedback. And here's what we're looking at. I notice we have a fairly large segment in others, so by all means, you're welcome to use the chat question box as we kind of get into more topics, as we get into more details on the subject. And then finally, or secondarily, what parts of the mitigation are you looking for some guidance in? And some feedback here is again useful. Appreciate very much you attending, and this feedback helps us expand on the information that we present specifically regarding the use of the EasyPower tools. So thank you there. Here's kind of how things look. Looks like we're kind of equally split out on this, and I appreciate the feedback. And as we start, I do want to kind of give you an advance notice of an announcement we're coming up with here towards the end of the session, because it deals with knowing more about technology that's available and how to utilize EasyPower to model that. And so I'll be having more details on this as we get towards the end of this morning's session. So it's something to look forward to. Where we'll be spending our time today is basically in the process of doing mitigation. That implies or pretty much verifies that we've already analyzed the system elements. And by doing so, we think we have, or have at least located, isolated areas that we need or have some concern over the elevated energy that could be released in a worst-case scenario. Well, now, what I mean by understanding the system is making sure we utilize the tools to consider what our alternatives are. And that's where the EasyPower value is extremely high, and where I'll be spending most of the time here as we get into the tools this morning. And then based upon those results, we face a decision about what to do. And those categories fall into three distinct areas. The potential solutions may vary widely based upon whether or not this is new construction, or usually older facilities end up having more headaches in this area. And this is where the arc flash suite, specifically the power protector or coordination module from EasyPower, can open up a lot of information that may not readily be available with any other form. And again, as we get into these, I'm going to spend more time using the tool to look at how the incident energy is calculated and how to take a first approximation on where I need to consider mitigation, because it's not always intuitively obvious if we haven't followed the process previously. I think it's important to note at this point, for several years now, NFPA has made a distinction between arc flash hazards and the risk associated when it comes to arc flash for any number of reasons. And I say that with the 2015 version, there's a very in-depth suggestion that once the assessment's been made, that you can analyze alternatives to deal with that. First of all, the assessment itself does not prevent an arc flash event. What it basically gives us is an estimate of the worst case energy or the energy in a worst case scenario if that arc were to happen at that location. On the other hand, the risk of that happening is proportional to the amount of activity, the type of work that's done while that bus is hot and exposed, the severity of the potential energy, and how to weigh all those in terms of what our alternatives are and the cost of mitigation in light of the risk evaluation. So I would direct you to NFPA 2015 because there's a decision tree there that not only gives some guidance in terms of weighting the various factors, but a decision tree to utilize in considerations and possibilities of dealing with that danger. Not necessarily mitigation, but some cases procedural or at least considering the risk versus potential harm. And it's in this addendum in NFPA 70E that they talk about the protective measures, and they divide the conversation up into 5 key areas. First would be engineering controls, which includes the technical devices or the devices used to mitigate energy, but it also includes protective barriers, safety personnel in attendance, and procedures that are utilized for working in a dangerous or hazardous area. Awareness devices, clearly indicating giving more information to not only the workers in the area, but anyone that may be entering the area in terms of changing processes or procedures because of a hazardous work in process. A lot of emphasis on maintenance, a lot of emphasis on training, and then the last consideration, and this is emphasized multiple times in NFPA 70E, is the focus on PPE itself. And I think that's primarily the message, that the PPE is the last line of defense, and while it's important, it's not the first place we go, because you're still having to deal with a very dangerous situation once you've decided just to suit up to high incident energy level. So now the need to mitigate energy in an existing facility kind of comes from several different sources most frequently. For instance, in older facilities that were designed before arc flash hazards were understood, frequently we'll find areas where the arc flash hazard is actually higher in a low voltage area than it is in high voltage or medium voltage. And again, that's because the protection, the faster, quicker acting protective devices were placed in the medium voltage sections, and we may have low fault currents that take exceedingly long times to trip protective devices for disconnects, creating very hazardous incident energy, and that's what you can actually see. These situations come up when you do a study. Another frequent case of concern is an area where a panel or a panel board has no barrier between the main circuit breaker and the bus that needs to have hot work, and consequently we cannot utilize the trip characteristics of that main protective device in calculating incident energy. And if that's the case, just changing that trip settings on that protective device won't do us any good. We need to consider how it can be incorporated in the safety process, or deal with making adjustments on any upstream device that would be the protective device. Another area where problems with mitigation arise in facilities that have been in operations for some time is exigent circumstances where the maintenance team may have made adjustments or replaced fuses during an off shift just to keep a system online or get it back up online quickly, and we can end up with incorrectly sized fuses even on one phase or all three, because that's what it took to kind of get the system back online, with the intent that at some point later that the fuse would be replaced with the correct value, and over time that might have been missed somewhere along the way. Again, that's the kind of thing we want to make sure we catch during an audit or a arc flash assessment. Another area where there's easily defined considerations in low voltage, actually 250 volts or less, systems where we've identified incident energy that's reported as elevated in an arc flash study utilizing the IEEE model. And that's a little different discussion, but the tools again let us visualize that as we get in and look at the OneLine diagram. And then, as I kind of mentioned, over time adjustable devices can be misadjusted because the maintenance team is trying to keep a particular device online, and they realize just by increasing the settings kept the breakers from tripping, but without really any concern about what that's done to incident energy calculations for arc flash. So in very frequently in those kind of situations we'll find that we're a hero because we were able to keep the plant up, but we're not realizing how much danger we're actually putting ourselves or our colleagues in if they have to work on that bus hot. So that brings us to looking at these OneLine diagrams in more detail. And far and away, probably the area that gives me the most heartburn is the need to do coordination in a very large or complex system, because the coordination process itself conflicts with mitigation. And the bottom line there is, if we have a OneLine diagram similar to this, where we're trying to coordinate with a large load in a remote feeder bus, then that means that we want the first inline breaker to trip first, the second breaker upstream from that point to trip next, and then in sequential order the trip devices upstream of that, which means if they're all similar type breakers, that we have to slow down the response time of the upstream breakers to accommodate that differential in time. And so what we've done at that point is unintentionally or otherwise raise the incident energy level above the coordinated feeder, if you will, and that may have given us headaches or heartburn when we have to go back and work on that bus hot. But it does give us a clue on how to deal with that in terms of being able to temporarily readjust and take advantage of technologies that let us set a temporary condition to lower those settings, knowing that we're not going to have transients downstream during the maintenance process. So again, that's stuff that we can look at with EasyPower. So let's jump into the tools and talk about this process specifically. One of the things that I like to point out is that just because we have a good reading, if you will, on a particular bus, that doesn't mean it's properly coordinated or even safe. The case in point is on this particular remote load, we have a nice low incident energy calculation, but everything around it is elevated, and so the question is why? And our first thought might be, well, we had to slow this particular breaker down. If we're looking at this, the incident energy calculated for this particular bus, if we come in and short just this bus alone, and then look at our arc flash results, we can see that that breaker was the protective device, and it tripped the on the arcing current of 13,800 amps. It tripped in 50 milliseconds. So then why is the bus upstream giving us a headache? If we look at that, we fault just that bus, we'll see that it's being tripped by the relay and not by this breaker upstream. So the point I'm trying to make there is if I say, okay, well, I can see that this bus is high, so what I really want to do is coordinate or readjust that particular bus, that breaker, the second breaker upstream. I go into coordination focus, and I plot these two breakers against the motor starting curve, and I can see, okay, well, this, if I fault this bus, looking at current, fault the bus, I can go to the TC curve and right-click and show the arcing current, and so this is what's being utilized to calculate the worst-case incident energy on bus 1. Now, one of the things that jumps out at me is like, well, so this isn't necessarily coordinated, but if I go and fault the bus upstream where I'm having my problem, and then look at the trip characteristics during arcing current, the tool says, well, I can't calculate it for this device. And the reason for that is this device is not the limiting factor when this particular bus faults. As we saw on the arc flash hazard spreadsheet, the device in question, or the device that's causing this incident energy calculation, is actually the relay. So that brings us back to kind of re-examining what's taken place. Even though we had reasonable incident energy on this bus, by looking at the trip time current characteristic curve, we can see we really don't have any protection or the proper settings on this downstream breaker to protect the motor. This short stubby line with the little bulb on the end is the thermal damage curve, and clearly the current and time can reach this point without the breaker ever receiving any stress. So if I go back to my readjustment of that curve of this breaker and then look at my incident energy, so I've actually haven't changed it at all because I'm using the instantaneous strip point for this breaker, but you can see now that I really have this upstream breaker miscoordinated altogether. So this is what I mean by an holistic view of my system and better understanding of my system. So what my arc flash hazard spreadsheet says is that this device is the limiting factor, or the device that will trip if this bus switchgear 2A faults. So to see that, I want to come up and plot all of these devices in this feeder loop, and what I see now that I've made my adjustments to my downstream breaker is that sure enough, this relay, which is this thin green line, not sure if everybody can see that. All right, so it's this thin green line that's actually being limiting factor for a fault in this area. So let's try this again. I'm going to fault this bus. I'm going to look for my arc flash current, and again the upstream breaker isn't going to show that to me. Let's right click on the relay curve and insert the arcing current, and we see that it's down here. Of course, it didn't come up with me. So the tool shows me the arcing current for the limiting device. And again, this is the relay, and clearly we have a miscoordination where the problem isn't so much the relay as it is this next upstream breaker. And I could have adjusted it all day long and see that it's really not solving my problem. Let's come back and show the instant energy. And the reason for that is where this arcing current, so I'm still on the arcing current that was plotted for the relay, and you can see that the vertical band on this breaker that I'm adjusting, which is BL2A, the magenta color, never gets to the point where it clears based upon this current, because we're in a vertical band on the breaker. And so that's why the relay trips next. So the moral of the story is, in terms of tripping this breaker, you can see as I readjust the long-term trip, or short-term pickup, I'm sorry, that it now brings into range the instantaneous tripping that can now be used for this particular breaker. Did that make sense? So I was able to lower this somewhat, and even though there wasn't an indication that it was even in the circuit, and by the way it was originally set. Now that's the kind of thing that may have occurred with somebody tweaking the relay settings. Now, I'm as guilty as anybody else. Once I'm in this kind of a mode, it's nice to know what Smart PDC would recommend for these settings, and by invoking Smart PDC, the tool comes back with these recommendations, which again took my incident energy up, but it did readjust the breaker, and so now I can see that I have clearance, and at that point I think I really want a power systems engineer to look at the coordination that we're trying to achieve for this downstream. It may be that there's other loads on this particular bus that need to be taken into consideration. All right, so the point I'm trying to make here is that we can be misled if we just look at one portion of the circuit or one report that's giving us incident energy calculations, and it's a matter of, and very frequently, an iterative process where we look at the continuous arcing current path for any particular load, and as we go back to the OneLine diagram, that is something we can actually achieve if we're in a coordination focus and we look at a sequence of events report. And to do that, I select the bus I want to fault. I'm in coordination focus. I'm looking for half cycle current. I fault that bus, and I can look at the trip times, and this tells me now that these two are set up for the same trip. This is set up for where this is recommended, where it should be relatively slow, and we're still out of whack on the relay. All right. The bottom line is looking at the bigger picture on a holistic basis is the value of the EasyPower tools. Now, the reason I kind of go through all that is when we get to this next series of presentations that I want to announce. For the months of June and July, we will be hosting on our Thursday technical webinar series a series of guest speakers who will be presenting alternatives in technology and hardware, and these will be the leaders in the industry in terms of arc flash incident energy mitigation, utilizing relays, breakers, fuses, and part of that discussion, if we don't cover it during the Thursday session, will be how to model that and how to show if that technology works in my particular OneLine diagram. So the options that we'll be including presentations on include maintenance mode, differential relays, zone selective interlocking, fuse alternatives, arc flash relays, and then combinations of some or all the above at various points. And what we're trying to do is give you the ability to consider what your alternatives are with a little bit broader knowledge of the technology that's out there in the market. Many of which are released only in the last 5 to 6 years. So it's fairly exciting stuff. That information's on the website, will be posted on the website, and we'll be getting that up, those schedules posted before the end of this week. Another option I wanted to mention is that the Tuesday refresher series for June, next week we will have the MCC modeling options and the different ways that you can either put more detail or less into your motor control center modeling and coordination possibilities. And then after that, starting on the 14th, we will begin a 4-week series titled Arc Flash Hazard Assessment and NFPA 70E Compliance. And they are 4 one-hour segments on how to step-by-step go through the data collection process, cover the analysis, modeling and analysis, then the report generation, and then dealing with how that information can be incorporated in training and maintenance scheduling. So that will be up on the website, and everyone's welcome to attend going forward there. The emphasis in that 4-week series is on what has changed in NFPA 70E and how that may affect a program that you thought was already under control, and what your alternatives are in terms of what that perturbation might be. Please look for that. And finally, a nice technology advancement that I think we are very proud of is the EasyPower on-site mobile app that we're going to evaluate in a 3-part data collection series isolated specifically on data collections. The first will be what data is required according to NFPA 70E and the IEEE 1584 model, how that data is collected utilizing a conventional method and then modeled. And then thirdly, go through the same workflow or the same process of data collection and recording and modeling, but this time using EasyPower On-Site, which is a tablet-based mobile application available now that allows you to collect the pictures, sketch the one line, and utilize spreadsheet templates. And then the biggest time-saving factor of all is that resulting file can then be uploaded into EasyPower and the one line constructed in the EasyPower format automatically, so you don't have to be an EasyPower expert during the data collection process. Appreciate everyone for attending today. By all means, EasyPower website has previously recorded training videos, the online instant demos available, as well as the 30-day download version if you request it. And by all means, refer to our previously recorded webinars as you kind of go through that evaluation. Finally, we have on the website now scheduling for regional training that's coming up in July here in Portland, in September up in the Vancouver, BC area, in October, Dallas, Texas, and then late October, a harmonics and dynamic stability class here again in Portland. All this, again, information is on EasyPower.com training page, and all the information regarding registration, costs, and what the schedules are included there. So I'm going to touch bases on some of the questions that we've seen. Thank you all for attending.